quadratic equations are everywhere in the real world. One common place they show up is projectile motion. Today we'll look at a ball thrown straight up and use a quadratic equation to answer when it will hit the ground. The height as a function of time can often be modeled by h of t equals negative 16t squared plus v naught t plus h naught. Here negative 16 comes from gravity when we use feet and seconds. If we throw the ball from the ground, h naught is 0. If the initial upward speed is 64 feet per second, then the model becomes h of t equals negative 16t squared plus 64t. Let's visualize this. We'll graph height versus time for times from 0 to 5 seconds. The horizontal axis is time in seconds, and the vertical axis is height in feet. Now, we'll animate the ball moving through time from 0 to 4 seconds. Notice it goes up, reaches a maximum, and then comes back down. Algebraically, to find when the ball hits the ground, we set h of t equal to 0. So we solve 0 equals negative 16t squared plus 64t. We can factor out the greatest common factor, negative 16t. That gives negative 16t times t minus 4 equals 0. By the zero product property, either negative 16t equals 0, which gives t equals 0, or t minus 4 equals 0, which gives t equals 4. These correspond to the times when the ball is on the ground, at the start, 0 seconds, and again at 4 seconds. Let's mark those points on the graph so we can see them. Summary: the quadratic model gave us the height over time. Solving h of t equals 0 told us the ball is on the ground at t equals 0 and t equals 4 seconds. In practice, quadratics help engineers and scientists predict trajectories and find maximum heights and times. Quadratic equations are used to design and predict real-world systems, from sports and ballistics to architecture and engineering. Whenever we see a curved path or need maxima and minima, quadratics are often the right tool.